Welcome everyone to the deep dive. And today, we're launching something pretty special, something really focused, our CSWIP 3.1 exam prep series. Now, for those maybe just tuning in or perhaps newer to welding inspection, CSWIP is the certification scheme for welding inspection personnel. And level 3.1, that's a huge step for anyone aiming to be a certified welding inspector.
Absolutely crucial, yeah.
So our mission today is pretty straightforward. We're going to tackle some multi-choice questions, kind you might see on the exam, but, and this is important, we're not just about spitting out answers.
No, definitely not.
We want to get into the why, unpack the thinking behind the right choice, pull out the key ideas, and hopefully give you a bit of a shortcut to really sharpening your understanding. Think of it as your personal study boost.
That's exactly it. True competence in this field, it isn't just knowing facts off by heart. It's grasping the principles underneath.
Right.
For the CSWIP exam, sure. But maybe even more importantly, for the real situations you'll face out on the job, you need to understand the mechanics, the metallurgy, the reasons why things are done a certain way.
Makes sense.
So our goal here is to give you that deeper insight, get you thinking critically, and hopefully build that confidence so you can tackle problems, even ones you haven't seen before, from a solid base.
Couldn't agree more. Right then, let's dive in. Question 1 takes us straight into mechanical testing. This is all about understanding what our materials can actually do.
Okay.
So the question is, toughness can be measured with which of the following mechanical tests? And your options are A, macro test, B, nick break test, C, tensile test, or D, Sharpie V-notch test.
Okay, this is a foundational one. The correct answer here is D, Sharpie V-notch test.
Sharpie V-notch, got it.
Now, let's talk about toughness itself. What does it actually mean in material science? It's often confused with strength, but it's different.
Right.
Think of it maybe like designing a car bumper. You don't want it to just be strong and shatter on impact.
Right. No, definitely not.
You want it to crumple, to absorb the energy of the crash. That ability of a material to absorb energy and deform without, catastrophically fracturing, that's toughness. It's resistance to fracture under impact.
Okay. The energy absorption part is key then.
Exactly. And the Sharpie V-notch test,
Yeah.
that's precisely how we measure it. We take a small standardized bar of the material, machine a little V-shaped notch in it. That notch acts as a stress concentrator.
Okay.
Then we often cool it down, sometimes way down, to simulate cold environments and then whack it with a heavy pendulum.
Right.
The machine measures how much energy that sample absorbed when it broke. High energy absorption means a tough material. Low energy means it's brittle. It's absolutely vital for things like bridges, pressure vessels, ships, especially if they operate in the cold.
That makes perfect sense. So comparing that to the other options then, why aren't they the primary measure for toughness? What do they tell us?
Good question. It's crucial to know what each test is for. So option A, the macro test. It's essentially a visual check. You cut a weld, polish it, etch it, and look at the cross-section.
See the structure, penetration.
Exactly. You're looking at weld profile, fusion, maybe big defects like porosity or cracks. It's about the overall geometry and quality, not really a specific mechanical property like toughness.
Okay.
Then B, the nick break test. You make a notch, like the name suggests, and break it open to look at the fracture surface. Gives you an idea of ductility, did it stretch before breaking, and helps spot certain internal defects.
Right.
But it doesn't quantify energy absorption. It's more qualitative.
More descriptive.
Right. And C, the tensile test. Super important, but for different things. You pull a sample until it breaks.
Measuring strength, right.
Yeah. You get yield strength, ultimate tensile strength, how much it stretches its elongation or ductility. It tells you how much load it can take before deforming permanently or breaking under a steady pull. So a material could be really strong in tension, but fail miserably in a Sharpie test if it's brittle.
Strong but not tough.
Precisely. And understanding that difference, knowing which test tells you what, that's fundamental for an inspector. You need the right tool for the job.
That distinction is so critical, especially, like you said, for safety critical parts. Choosing the wrong test or misinterpreting the results, well, the consequences could be serious. A strong brodge that shatters in the cold isn't much use.
Exactly right.
Okay, fascinating stuff. Let's move from the material itself to the act of welding, and specifically the welder's skill. Question 2 asks about manual arc welding challenges. Which of the following welding parameters are the most difficult to control during the welding operation using a manual arc welding process? Options: A, travel speed, B, deposition rate, C, current, D, arc length.
Right. This is a classic we're highlighting welder skill. The answer is D, arc lengths.
arc length. Why is that one so tricky?
Well, think about manual arc welding, stick welding.
Uh-huh.
That electrode, it's constantly being consumed, right? It gets shorter and shorter as you weld.
Okay.
So the welder has to continuously, smoothly feed that electrode in towards the workpiece to keep the distance, the arc length, consistent. It's not something you just set. It's a dynamic, moment-by-moment adjustment based purely on feel and observation.
Ah, I see. It's constantly changing because the electrode is changing.
Exactly. And if that arc length varies, it messes everything up. Too long an arc, the voltage jumps around, you get more spatter, less penetration, maybe a wide, flat bead. Too short, you risk sticking the electrode or stubbing out, which can cause lack of fusion or other defects. It's a real balancing act.
It sounds incredibly difficult to maintain perfectly, like trying to draw a straight line while your pencil keeps shrinking.
That's a great analogy. It really is. Now compare that to the others. Travel speed, ace. Yes, it's crucial. But you get visual feedback. You see the weld pool forming behind the arc. You adjust your hand speed accordingly.
Okay, you can see it.
Deposition rate, that's mostly linked to your current setting and the type and size of electrode you chose. The welder's technique influences it a bit, sure, but it's not the primary thing they're actively controlling moment to moment, like arc length.
Right, it's more predetermined.
And current, see, you set that on the machine before you start, dial in your amps, and the machine delivers it. The welder just needs to maintain technique at that current. So while managing all these is skillful, that constant, tiny adjustment of arc length is the one that's purely down to the welder's hand-eye coordination and feel.
Wow, that really highlights the artistry involved, doesn't it? It's not just science. It's this incredibly refined motor skill developed over years. You see a perfect weld bead, and you know that reflects immense concentration on details like arc length.
Absolutely, it's a craft.
Okay, so we've talked about welder skill. Let's look at the result, the finished weld. Question 3 is about visual inspection clues.
Reading the signs.
When conducting a visual inspection on a butt weld, you notice an excessive chevron-shaped cap ripple. This may indicate which of the following options. A, incorrect electrode. B, excessive travel speed. C, incorrect preheat applied. D, that the welding has been carried out in the PF welding position.
Right, those visual cues were like the weld telling you its life story. And an excessive chevron-shaped cap ripple, that's a big clue. The correct answer here is B, excessive travel speed.
Okay, excessive speed. What does that look like exactly? Chevrons. Like V-shapes.
Yeah, imagine V-shapes pointing back towards the start of the weld, but they're really elongated, pointed, and spaced quite far apart. Not the nice, rounded, evenly spaced ripples you want to see. It looks rushed.
Like skid marks, almost.
Kind of, yeah. It happens because the welder is moving the arc too quickly for the amount of heat being put in. The molten weld pool doesn't get enough time to flow out, settle down, and solidify smoothly.
It freezes too fast in that pointed shape.
Exactly. Yeah. The arc moves on before the puddle can properly form and flatten. And this isn't just cosmetic. It often indicates that other things might be wrong too, like maybe not enough fill or poor fusion at the root because the heat didn't penetrate properly.
So it's a surface sign of a potentially deeper issue caused by going too fast. What about the other options? Why aren't they the primary cause of this specific ripple?
Good question. Let's see. Incorrect electrode.
Oh.
That usually shows up as maybe arc instability, excessive spatter, maybe the final weld chemistry is wrong. But it doesn't typically create that specific elongated chevron ripple pattern.
Okay.
Incorrect preheat.
Yeah.
If your preheat is wrong, especially too low on certain steels, you're more likely looking for cracking, maybe porosity, or just a generally poor bead shape because the heat flows off, not usually this specific ripple.
Right, different symptoms.
And welding in the PF position that's vertical up, that definitely affects how you weld. You need techniques to counteract gravity. You might get a slightly more convex bead, perhaps. But again, the excessive chevron ripple itself, it still points directly back to travel speed being too high for the conditions, whatever the position.
It's amazing how much you can deduce just by looking closely. That ripple pattern is a direct fingerprint of the process speed, really emphasizes the power of good visual inspection.
It's your first line of defense, and often the most informative if you know what to look for.
Okay, let's move on. We've looked at tests, process, and visual signs. Question 4 takes us into weld design, specifically thinking about long-term performance and fatigue. And this one you mentioned has a bit of a twist.
Yes, this one often trips people up.
Which of the following fillet-welded T-joints would have the highest resistance to fatigue fractures, assuming material, welding process, filler material to be the same? Options are A, a convex fillet weld throat thickness 10 millimeter, B, A miter fillet weld throat thickness 8 millimeter, C. A concave fillet weld throat thickness 8 millimeter, or D. Both A and B if they have the same throat thickness. And the hint was the biggest one isn't necessarily best for fatigue.
Exactly. And the answer, perhaps counterintuitively for some, is C. A concave fillet weld throat thickness 8 millimeter.
The concave one, even though it's smaller than option A.
Yes. And the reason boils down to stress concentrations. Fatigue failures from repeated loading and unloading, are incredibly sensitive to sharp corners or changes in geometry. They almost always start at these high stress points.
Okay.
Now think about the weld toe, that little transition point where the weld blends into the base plate. A convex fillet weld, option A, even though it's bigger overall with that 10 millimeter throat, tends to create a sharper angle right at that toe.
Right, it bulges out.
It bulges out, creating a steeper transition. That sharp corner acts like a little notch, concentrating the stress every time the joint is loaded. It's a prime spot for a fatigue crack to start, even with more weld metal there.
Like a weak link in the chain, geometrically speaking?
Precisely. Now compare that to the concave fillet weld, option C. Its profile curves inwards, creating a much smoother, more gradual transition at the weld toe.
More like a gentle ramp than a sharp corner.
Exactly. That smooth profile distributes the stress much more evenly, reducing that peak concentration right at the toe. This makes it significantly more resistant to fatigue cracks starting, even if the nominal throat thickness is slightly less, like the 8 millimeter here compared to the 10 millimeter convex one.
Wow.
The miter fillet B is sort of the in-between, a flat face. Better than convex, generally, but it doesn't give you that positive stress-reducing benefit of the concave shape.
That's a real aha moment. So for fatigue, the shape of that transition, that weld toe geometry, is actually more critical than just the sheer size or throat thickness. Less sharp corner equals more life.
That's the essence of it for fatigue design. Smooth transitions are key.
Fantastic insight. Okay, one last question for today. Let's look at thermal cutting, another process closely linked with welding and managing its effects.
Right. Dealing with the heat.
Thermal cutting. Local hardening can be reduced by which of the following? Options. A. Increasing the cutting speed. B. The use of propane as a fuel gas. C. Preheating the material to be cut. D. All of the above.
Okay, so local hardening, what are we talking about? When you thermally cut certain steels, especially higher carbon or alloy steels, the area right next to the cut gets very hot, then cools down very quickly because the surrounding metal acts like a big heat sink.
Rapid cooling.
Very rapid cooling. And that can cause the steel in that narrow band, the heat-affected zone, or HAZ, to transform into martensite.
Martensite. That sounds familiar. Very hard, right?
Extremely hard, yes, but also very brittle. Think glass hard. Not something you generally want on the edge of a component as it's prone to cracking.
Okay, so how do we avoid that?
The most effective way listed here is C. Preheating the material to be cut.
Preheating, how does that help?
Well, if you raise the overall starting temperature of the material before you cut it, then after the cutting flame passes, the cooling rate of that HAZ is significantly slower.
Ah, because the surrounding metal is already warm.
Exactly. The temperature gradient isn't as steep. That slower cooling gives the steel's microstructure time to transform into tougher, less brittle phases, like perlite or bainite, instead of that hard martensite. You're essentially managing the cooling curve.
So preheating is like giving the material a gentler cool down, avoiding that thermal shock that creates brittleness.
That's a great way to put it. Now, quickly on the others. Increasing cutting speed, A, might actually increase hardening sometimes by reducing total heat input, but still having rapid cooling right at the edge. It's not a reliable way to reduce hardening. And using propane, B, versus, say, acetylene, different fuel gases have different flame characteristics. But changing the fuel gas isn't the primary method aimed at controlling the metallurgical transformation caused by the cooling rate. Preheating directly addresses the cooling rate issue.
Got it. So preheat is the targeted solution for mitigating that local hardening. It really links back to understanding the material science, the heat transfer. It's all connected.
It absolutely is. Welding, cutting, material behavior, it's all intertwined.
Well, that brings us to the end of our questions for this deep dive. We've covered a lot of ground, haven't we? From Charpy tests and toughness.
And arc length control.
To reading chevron ripples, understanding fillet profiles for fatigue, and controlling hardening during cutting. Really valuable insights for anyone prepping for that CSWIP 3.1 exam. And hopefully we've emphasized the why, not just the what.
Definitely. And maybe a final thought to leave you with as you continue studying or working. Think about that interconnectedness, how a seemingly tiny detail, A slight waver in arc length, the exact shape of a weld toe, the preheat temperature chosen, how all these seemingly small things can add up to determine if a massive structure will perform safely for its entire design life. How does knowing how critical these details are, change how we approach our role as inspectors? How much more vigilant and knowledgeable does it compel us to be?
That's a powerful point. It raises the stakes, really. A reminder of the responsibility involved. Excellent food for thought. Keep asking those questions, keep observing, and keep learning. We wish you all the best with your studies and your work out in the field.
Good luck, everyone.
Until next time on The Deep Dive.